All right, so now we're going to play the game. Is it aromatic?
Yes.
And here are the rules. Got to be cyclic, fully conjugated, have the right number of pi electrons, 4n, satisfy the 4n plus 2 rule. Yes.
Did you say fully conjugated meant that every atom is involved with pi bond?
Every atom in the ring is involved in. No, you can't. That rule will not work. Every atom in the ring doesn't have to be involved in the pi bond, but it does have to be conjugated, meaning it's sp2 hybridized, has a p orbital that can line up with the others in the molecule. As an example, is it aromatic? Are you sure? Don't let me, truth is truth, whether or not I agree with it, right? So that's aromatic, yes. Let's verify that it meets all the criteria. Is it cyclic? Yes. Is it fully conjugated? What do we mean by that? Well, each of these atoms is sp2 hybridized. How can you tell this nitrogen is conjugated to the others? You got a lone pair adjacent to a pi bond. Also, another clue is you can draw resonance structures which would put the lone pair on one of the other atoms. Okay. And it's got how many electrons are participating in the pi system? 6. Okay, good. Cyclic, fully conjugated, has the right number of pi electrons. Okay. How about that? Aromatic? No. It's cyclic, but what does it fail at? It's not fully conjugated. In fact, if it's not fully conjugated, there's no point in worrying about the Huckel rule. Don't bother counting electrons if it's not fully conjugated. Okay? You can tell this is not fully conjugated because you have these sp3 hybridized atoms. There's no p orbitals on those to participate in the pi system. Okay, let's see. Doing pretty good. Let's try aromatic. Okay, I'm hearing yes and no. So that means some of you need to learn something. Actually, we all need to learn something in our lives, but there is a specific concept we need to learn here. And that is which electrons count for the pi system. Yes, this molecule is cyclic. Yes, it is fully conjugated. Then, does it have the right number of pi electrons? Now, some of you were counting 2, 4, 6, 8. Others were counting 6. Okay, those of you who are counting 6 are correct. How do you know not to count the lone pair? Go ahead. Lone pair, what do you mean? Cannot go into the ring? Ah, how do you know that the lone pair is in an sp2 orbital? Yeah, the p orbital on that nitrogen. It's clear that the nitrogen's sp2 hybridized because it's surrounded by 3 things. The p orbital on that nitrogen is already accounted for in our drawing, and therefore these two, the lone pair on that nitrogen, are in an sp2 orbital, not part of the pi system. Let's look at a side view of this molecule, sort of tilting it on its side. Here's the nitrogen. That represents the edge that's jutting out towards us. The lone pair is in an sp2 type orbital that's orthogonal or perpendicular to the pi system of orbitals, right? Which we could draw here, here, here. I'm just drawing the lowest energy combination of that pi orbital where everything's overlapped on adjacent atoms in phase. Do you see how that sp2 orbital with the lone pair is perpendicular to the pi system? Orbitals that are perpendicular don't interact. That lone pair is not involved in resonance. In fact, another clue is you cannot draw a valid resonance structure that delocalizes that lone pair into the ring. So, moral of the story, Huckel rule you can't apply without accounting for which electrons are even part of the pi system to begin with. Okay? This is a particular problem with rings that involve heteroatoms, because heteroatoms often have lone pairs on them. So yes, indeed, this is this molecule is aromatic. It's called pyridine. Let me give you a related, what we call a heterocycle. This is a ring of some size that has heteroatoms of things other than carbon or hydrogen, and there are lone pairs. I draw that and I almost want to laugh. I almost want to give an evil. Not amused. You can hear that in your head when you take the exam. Okay. Is it aromatic? Okay. You are correct. It is. It is cyclic. It is fully conjugated. Now, I know that the pi bonds count, but what about the lone pairs? Which are part of the pi system and which are not? Just the one on the O? So it's this one, and this one. I don't count this one on the nitrogen for the same reason as pyridine, right? Go ahead.
I have a question. So with this, wouldn't there be then like no way for there to be too many electrons for like the pi system and stuff like that? Like because if everything's sp2, there's only like one p orbital like that they could be in. So like it only wouldn't be aromatic if it had too little.
So yeah, I guess the question is there a way to, you're maybe envisioning ways in which you could be not aromatic because you have too few, but not too many?
Yeah, like for example, the one you gave where we just said no, where like there was like 2 pi bonds.
Right, there we didn't even count, we didn't even worry about the number of electrons because it was not fully conjugated.
Yes.
What we need to deal with though is what if it's fully conjugated but has the wrong number of electrons? And I haven't given you any examples of that yet, but I will. Okay, how did you know? So you knew not to count this lone pair on the nitrogen because the nitrogen's sp2 hybridized. The p orbital's already accounted for in the pi bond that nitrogen's in. So the lone pair must be in an sp2 orbital, and we don't count electrons that are in sp2 orbitals. That's the same reason why we don't count the electrons in the sigma bonds, right? What about the oxygen? How did I know to count one of those but not both? Same reasoning, right? Only oxygen is bonded to 2 things when it's neutral instead of 3. So that oxygen is surrounded by, let's see, 4 groups, it has to be sp2 hybridized so that one lone pair can be in a p orbital so that it can participate in resonance. But if one lone pair is in a p orbital, the other must be in an sp2 orbital. Yeah.
Is that because that orbital faces up and down?
Yeah.
Whereas-
Yep, exactly. That p orbital is, so from our perspective, the p orbital that lone pair is in is above and below the page. The other one's in the plane of the page pointing outward. Yeah.
And like removing the possibility of conjugation there, that oxygen would just be sp3 hybridized. It's only has that the p orbital with electrons because it's stabilizing.
Right, so I think your question is, what if I did this? Yeah, that you would say that oxygen's sp3 hybridized. Yeah, its conjugation pays for it to be sp2 hybridized. Because you're right, normally surrounded by 4 groups, you'd want to be sp3 hybridized to minimize electron repulsion. Being sp2 hybridized when you're adjacent to a pi bond allows for resonance stabilization. Yeah. Okay, so yes, this has 6 pi electrons, and that satisfies our 4n plus 2 rule. So with oxygen, a maximum of 1 lone pair can be involved in the pi system. Okay. Oh, right, this one's fun. Aromatic or not. Okay, yes. It is aromatic, and 2, 4, 6. I don't count this lone pair for reasons we've discussed. Why do I count that one? Because that nitrogen is sp2 hybridized. You can account for each of the sp2 orbitals in the sigma bond. So the only place for that pi, for that lone pair to be, is in a p orbital where it's conjugated with the other electrons. Okay, so work through that. Get familiar with, get more than familiar actually. Get I don't know, mastery or get comfortable, but even more than comfortable. Get used to these contexts for nitrogens and oxygens in aromatic rings. Look for the nitrogen that's involved in a pi bond and has a lone pair. Look for the nitrogen that's not involved in a pi bond but has a lone pair. Those are 2 different situations, yeah.
And so the character of this as we go to the conjugated base, is it still aromatic when we remove the
Conjugate base?
Yeah, conjugate base of this.
Yeah, it would still be aromatic because you haven't changed the pi system at all. Similarly, you can go to the conjugate acid, you haven't changed the pi system at all. One great way to ask this question about whether test your understanding on aromaticity is to ask, which of those 2 lone pairs is more basic? Which of those 2 lone pairs is more basic? B, because if you protonated A, you'd destroy aromaticity. You'd prevent it from being fully conjugated, right? Suddenly, if I add a proton to A, whoops, now that nitrogen's sp3 hybridized. The molecule's no longer fully conjugated. So if the conjugate base loses, if the conjugate acid loses the stability of aromaticity, that set of that lone pair must not be very reactive. In contrast, for B, I can add a proton there, and it does nothing to the aromaticity. Yeah.
So, like, for example, for the last drawing with the oxygen with 2 lone pairs, it was my understanding that if an oxygen is bonded to 2 molecules and then has 2 lone pairs, it's sp3 hybridized.
Uh-huh.
What am I missing
You're missing resonance stabilization. So you're absolutely right, except when you can do resonance.
Oh, okay.
The only way for that oxygen to participate in resonance is conjugation. It involves p orbitals adjacent to each other. So in order to get that stabilization, the oxygen hybridizes sp2 so that one of the lone pairs can be in a p orbital where it can participate in resonance.
Okay, got it.
Yep.
So if you were to add a pi bond on this comment you just drew on the right to either one of those, so it could do it. Now it's sp2, right?
I think so. It's a decent bet. Yes. Yeah. I mean, there's more to say there. Hybrid molecules don't know about hybridization. Hybridization is a tool we humans use to try to explain bonding in ways that are easier to understand. You can throw out the concept of hybridization entirely. You have to also let go of the concept of bonds and just look at molecular orbitals for all of the atoms being delocalized across the whole molecule. But that gets a little annoying, frankly. And the focus on individual atoms and bonds is useful for organic chemistry. But I would say that, yeah, lone pairs adjacent to a pi bond are going to be, one of them is going to be in a p-type orbital so that you can engage in resonance. Yeah. All right. So let's talk situations where molecules might have the right, be cyclic and fully conjugated, but have the wrong number of pi electrons. And this will also give us a chance to talk about what aromaticity really means. So, cyclobutadiene. Aromatic? No. How many electrons, pi electrons does it have? 4. And the 4n plus 2 rule says it's got to have 2, 6, 10, etc. All right, so wrong number of pi electrons. It is cyclic, and it is fully conjugated. So if you're cyclic and fully conjugated, but you have the wrong number of pi electrons, that is 4n instead of 4n plus 2, that is no longer just not aromatic, that is especially unstable. And it's called anti-aromatic. And let me show you what I mean by especially unstable. To understand this, you really need the MO picture. We're not going to draw those MOs, but we're going to use the Frost cycle, or circle, so whatever. Whoops. Oh, yeah. And then let's inscribe a square on the inside of the Frost circle. Remember that no. Sorry. That's close enough. So anytime the point of the polygon touches the circle, you've got an energy level of an orbital. So here, 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 and here. Remember that the midpoint is the energy of non-bonded p orbitals. And now we fill up the diagram with the available electrons. what do? I only have 2 electrons left. There's a rule from general chemistry you learned. It's actually based on quantum mechanics, and if you want to know more, you should take my 552 class. You get a bit of a bonus stabilization when you have parallel electrons with parallel spin. So you fill each of these orbitals with 1 electron, same spin, then you're out of electrons. So you've made a molecule where you supposedly have 2 pi bonds, but actually you only have 1, and the other 2 electrons are not even in a bond anymore. They're at the level of non-bonded atomic p orbitals, and it's a diradical. Radicals, as you learned in 351, have some unique reactivity patterns. So in fact, this molecule, as we've drawn it, cyclic, fully conjugated, all the bonds equal length, wrong number of electrons, is as reactive as a diradical. So whereas benzene is more stable than you would expect for 3 isolated pi bonds, cyclobutadiene is less stable than you would expect for 2 isolated pi bonds. It reacts as a diradical. And in fact, you cannot really observe this molecule under normal circumstances. In fact, molecules like cyclobutadiene that would be anti-aromatic often distort their shape to avoid being diradicals. So one thing cyclobutadiene does is it, instead of being a perfect square, it will lengthen 2 of the bonds and twist a little bit out of conjugation, and then it's more like 2 isolated pi bonds. It's not so bad. You can observe cyclobutadiene. It's been the quest of a generation of organic chemists to observe cyclobutadiene. You can do it in a matrix of solid argon at 4 Kelvin, which is kind of hard to do. Or there was a Nobel Prize winning chemist, Professor Donald Cram at UCLA, who invented basically a molecular container, a box that he built out of atoms. I used to have a model of it in my office. I think I took it apart. But in any case, he put a precursor to cyclobutadiene in the box, and then you could convert that molecule into cyclobutadiene with a laser, right wavelength of radiation. It would expel CO2 and become cyclobutadiene. And the box protected cyclobutadiene from reacting with other stuff. And so you could, and this is again a very tiny molecular box, but you could observe cyclobutadiene at room temperature indefinitely because he had protected it inside this container. It's sort of gee whizology, because it's kind of like, okay, great, you did it, yay, and now what? And not sure. But actually, the idea of designing molecules that bind other molecules has been an important part of the last 30 or 40 years of organic chemistry and chemical biology. It's led to a lot of important new discoveries and drugs, and so for that, Professor Cram won the Nobel Prize back in the mid '80s, and it's kind of a neat achievement to be able to take something that's this unstable and manage to have it sit on a bench top and stare at you because you put it in a protective container. All right, so anti-aromaticity is a thing if you have the wrong number of pi electrons. Let's see. So now let's use this concept. Is it aromatic? Is it not? There's 3 possible answers: aromatic, not aromatic, or anti-aromatic. Yeah?
Is it ever possible for a 4-membered ring to be aromatic?
Could a 4-membered ring be aromatic? Well, you tell me. What would you have to do to get the right number of pi electrons?
I'm not sure.
You got to add 2 or take away 2, right?
Yeah.
So a question you could ask then is this aromatic, and if so, what does that even mean? Actually, let's just What that means, yes, it's aromatic because it only has 2 pi electrons. It satisfies the criteria. That means it's more stable than a dication of that size would otherwise be. Okay. Yeah. And so, let's see. Let's use this to do a few comparisons between. Actually, without answering the question aromatic or not, we can use these concepts to help us predict some properties of organic molecules. So there's cyclopentadiene. Oops, I used to be good at 7-membered rings. Students in previous semesters have likened my 7-membered rings cycloheptatriene to a sad robot.
Oh yeah.
Although I guess the 5-membered ring looks kind of sad too. I don't know. Maybe evil robot. Anyway, without telling you pKa numbers, which of those two is more acidic? Are you sure? So when comparing acidities, always draw, this is something you should have learned from 351, always draw the conjugate base. Do you have any reasons to suspect one of these is more stable than the other? So the top one is cyclic. Both of them are resonance stabilized, right? You got that going for you. Cyclic, fully conjugated. How many pi electrons do I have for cyclopentadienyl anion? 6. How about here? Cyclic, fully conjugated, but 8 electrons. So this anion would be anti-aromatic. This one would be aromatic. Now, use your reasoning with conjugate bases. A less stable conjugate base has a less acidic conjugate acid. So cyclopentadiene is more acidic than cycloheptatriene. Okay, let's ask the question in a slightly different way. Same players, different structures. I want you to consider reactivity in an SN1 reaction. And your contestants are that guy, and that one. Maybe we'll try to make the sad robot look wistful? I don't know. Okay, SN1 reactivity. Which one reacts faster in an SN1 reaction? To do this, we're not drawing the conjugate base this time, we're doing what happens in an SN1 reaction. The leaving group leaves, so draw the carbocationic intermediate. Yep, good. I think what happened is I bragged about drawing 7-membered rings too much, and then it became harder. Got the 7-membered ring yips. Okay. Which carbocation is more stable? Okay, this one has 4 n electrons, 4 electrons. This one has 6. So we've got both are cyclic and conjugated, but wrong number of electrons, so that's anti-aromatic. That's especially unstable. Cyclic, conjugated, aromatic because it has the right number of electrons, unusually stable for a cation. Remember that in an SN1 reaction, the transition state resembles the carbocationic intermediate because of the Hammond postulate. Therefore, the more stable carbocation should react faster. Okay? All right. Questions about that? No? Yeah.
So it's more stable because it can be in that state for longer and it's not a problem? Is that the idea?
Well, compare, let's see. To your frost circle for the cyclopentadienyl cation, you're a diradical. Whereas if you do the cycloheptadienyl cation, all of your bonding orbitals are filled. Yep. So yeah, that means that this cation is more stable than this one. Yeah, go ahead.
So what if you're comparing, let's say, the top cation to a molecule which is 1 pi bond or no pi bonds?
Yeah, it's a good question. What if you're comparing this versus only 1 pi bond or no pi bonds? Then I think the comparison gets hard to make in a way that wouldn't involve experiments or calculations.
Okay.
Yeah. I would say, if I were guessing, I would say for the anti-aromatic one, 1 pi bond versus the 2, it's probably better this way because at least it's resonance stabilized, but it's not especially unstable. And but I don't know how to compare this one to the one without the pi bond. Yeah. Okay. I guess the smallest aromatic system you could think of would be maybe this one. Which I think starts to sort of look like the little aliens from Toy Story. The claw. Let's see. Now let's maybe do some trying to see whether there's any useful challenge problems. All right, I think we've done what we need to do there. What I want to do now is introduce, we've spent a lot of time telling you how special benzene is and unreactive it is. but it turns out you can do reactions with it. You just need, and you can use benzene as a nucleophile, but you just need a really reactive electrophile. And recall that at the beginning of class today, I gave you an example of a reaction of an alkene with benzene. I'm sorry, with an electrophile. And alkenes undergo addition reactions, right? So you can use Br2 to make the vicinal dibromide. You can do a reaction with benzene and Br2, but you need something else to make the reaction work. So we're going to put a box there to indicate that we need something else. But even then, what the product is going to be is not an addition product, but we're going to get a substitution product. And the reason we're going to get a substitution product is because the drive to keep aromaticity is so strong that we're going to get to an intermediate where we've added one bromine, and then we're going to do something else to get aromaticity back. And that's going to be the theme for all of these reactions that we're going to talk about in the next chapter. They are all called electrophilic aromatic substitution reactions. But the key is substitution rather than addition. Alkenes do addition reactions. Benzene rings generally don't. They do substitution reactions, and the substitution part is all about once you've added the electrophile, you've got to lose something else in order to restore aromaticity. So let me take you through an example of just sort of a general mechanism for these types of reactions. Imagine you have a benzene ring and you have some electrophile. We're not going to say what it is. That's why we're just calling it E with a positive charge. We can show one of the pi bonds, and they're all identical. We can show two of the pi electrons from benzene. Actually, they're not identical. We just went and showed that. You have two that are lowest energy and two that are higher energy. So one of these two degenerate pairs of higher energy electrons. But in terms of the arrow pushing, we can choose any of the pi bonds in the benzene ring, is going to attack the electrophile. Because we're not specifying what the electrophile is, we don't have any arrows to do right in there right now. That's going to generate an intermediate that looks like this. And as with alkene chemistry, the atom that was involved in the pi bond, sorry, you've got two atoms, 1 and 2, that were involved in the pi bond. The electrophile goes on one of them, the positive charge goes on the other. As with alkene chemistry, where there was some regioselectivity issues, which atom gets the electrophile, which atom gets the positive charge, there are going to be those issues later on with some more complicated reactions with benzene. We've chosen a simple one because carbons 1 and 2 are identical, so that it doesn't matter. Notice that this intermediate is no longer aromatic. Why is it not aromatic? Not fully conjugated. You don't even have to worry about the number of electrons because one of those atoms, this one, is Sp3 now. Okay? Now we've got an adjacent positive charge. Final exam question. Which other atoms share that positive charge? That one and that one. 4 and 6, right? That's going to be important a little bit later. Now, once we've added that that electrophile, can you think of a reaction we could do that would restore aromaticity? Elimination reaction, right. You've got a proton adjacent to a positive charge. We just need some base, and it doesn't even have to be a very strong one. Turns out this proton is crazy acidic because when it's removed, the conjugate base is aromatic. So that's going to be the mechanism. We're going to do a lot of different reactions in this chapter. They are all going to involve that basic mechanism. Add the electrophile, generate this intermediate that is not aromatic, then remove the proton and get the substitution product. In doing this, we have basically swapped out our electrophile for our proton. And so that's where we get the idea of a substitution reaction. Okay? Let me show you a specific example of this. This reaction is called aromatic halogenation. And I'm going to fill in the box that we were missing up here when I indicated that we need something to make the reaction go. It turns out for most benzene rings, Br2 is not electrophilic enough, so we need a Lewis acid. We need to add a Lewis acid to help soup up bromine as an electrophile. And the Lewis acid of choice is iron tribromide, FeBr3. You don't need to worry about the structure of FeBr3. It's iron in the +3 oxidation state, and that means that you've got some empty d orbitals on iron that can accept electrons. We're basically going to do nothing with transition metal chemistry until the very end of the semester. And even then, I'm sort of hoping I talk too long about other stuff so we don't have time for it, because I'm not very good at it. But think of iron as having empty d orbitals that can accept electrons. So what happens here is that lone pairs on one of the bromines will actually do a Lewis acid Lewis base thing with FeBr3, attacking one of the empty d orbitals on iron to create a new bond. What that does is it puts a negative formal charge on iron and a positive formal charge on bromine, and it basically turns all of this into an excellent leaving group, such that benzene can attack the bromine, breaking the bromine-bromine bond. You've seen pi bonds attack bromine before. That was really easy, right? Breaking that bond, and then this one goes there. We're just making that process easier by making the leaving group not be Br minus, but be something that's neutral. Once we've made that new bond between one of the carbons of benzene and the Br, at that point, we don't need to worry about what the leaving group was anymore. We get an intermediate, whoa, nope, put the double bonds in the wrong spot. We get an intermediate that looks like this, and then some base, it could be actually Br minus or, but we don't really care what it is, removes this proton to generate the substitution product. Oops, yikes. Okay, so that's reaction one. And you can do this with chlorine as well. The choice of iron as a Lewis acid catalyst, there are other things you could choose. The choice to match the identity of the halogen with the identity of the group on the iron is something your text always does. I'm not sure how important it is. Okay, I'm sorry. Whoa, you guys should have told me to shut up. We are done. We will see you on Wednesday. Okay. Right. So, if our y-axis is energy, you have one lower energy orbital, and then you have two orbitals that are equal in energy that are higher up. Sorry. We call orbitals that are equal in energy, there's a mathematical term for that. The term is degenerate. Okay? That's not an editorial on their moral merits or failings. It just means they're equal in energy. You can continue. It's not, and again, I would never ask you to generate these pi orbitals for benzene from scratch, but I want you to see them so you can understand a rule that we're going to introduce a little bit later. It turns out that the next two higher energy orbitals are also degenerate. There are going to be two independent ways in which we can have two nodes in a system like this. So one of the ways is to have them be between the atoms. Maybe that's not the best way. That's not right either. Maybe it is. Anyway. Clearly not getting them from my head. All right, so we'll call this one pi 1, pi 2, and pi 3. You can look in your text and it will show you the structures of pi 4 and pi 5. Pi 6 is simply going to be the one where they're all out of phase, so we have wave function sign changes between each atom for a maximum possible number of nodes. I'm sorry, I don't know why it's not occurring to me what the actual shapes of those orbitals for pi 4 and pi 5 should be. They are degenerate as well, and they have two nodes instead of just one. We could figure it out. It's just probably not worth our time. But the point is that benzene has 3 pi electrons. I'm sorry, benzene has 3 pi bonds drawn there. Three sets of.
Professor?
Yes.
I looked it up. It's you were right with the X, and then it's just
A D?
a T. I get it.
Okay, I'm confused, but that's okay. So I've seen it before. Let's see, it should be something like this.
Yeah.
Okay, so sort of 2 nodes.
Yeah.
Or you could alternatively have done it.
And then the
Yeah.
other one is you take your pi 3 and you add a node between the 6 and 5.
Okay, thank you. So clearly if I can't do it in front of you, then I can't expect you to do that on an exam, right? I mean, I'm decently comfortable with my own hypocrisy, so, but, like that? Okay. Good. And you can go through these, thank you. You can go through these and actually count up, again, bonding interactions versus anti-bonding interactions. What you come up with is, let's see, 6 bonding interactions for the lowest energy orbital, 2 net bonding interactions for the next pair. I see basically overall 2 anti-bonding interactions here, and then 6 anti-bonding interactions here. Is that fair enough? Okay. Now, 6 electrons involved in the pi system. We call this extended bunch of orbitals a system of orbitals, a pi system. 6 electrons involved in the pi system. You start with the lowest energy orbital, you fill it with 2 electrons. The next higher energy ones then get filled. You in benzene have 1 lower energy and then orbital, and then pairs of degenerate higher energy orbitals. So if you have 6 electrons in benzene, you are able to fill all of the bonding orbitals. If we use our dotted line to indicate the location of sort of where non-bonded p orbitals would be, with 6 electrons, you fill all of benzene's bonding orbitals and none of its anti-bonding orbitals. Okay. And if you do the math, it turns out that relative to 3 isolated pi bonds, benzene has almost a full pi bond's worth of extra stability, even though it's only got 3 pi bonds. Now, molecules like benzene that are cyclic fully conjugated, meaning each atom is in that ring is involved in the conjugated pi system, and that have the right number of pi electrons, where all of the bonding orbitals are filled, terrible penmanship today. Put these things together and you have a molecule that is called aromatic. Now that does not refer to anymore to the smell of the molecule, though originally benzene does have a distinctive smell, and so benzene molecules like it sometimes are volatile and have an interesting smell, and that was why the word was originally chosen. But we use the term aromatic, or that's the adjective. The noun is aromaticity, the state of being aromatic, are cyclic, fully conjugated, and they have the right number of pi electrons to fill the bonding orbitals completely with no empty or half-filled orbitals. They enjoy this special stability. The stability comes from the fact that when you get both resonance stabilization and this bonus pi bonded stability you get because of your extra overlap between the orbitals on the end. And so if you satisfy these criteria, you are similarly stable to benzene. And there are a lot of molecules that do this. And what we're going to do now is sort of go through and identify molecules that are this way versus aren't this way. However, there's kind of a neat rule you can use. The rule for the right number of electrons is called the Huckel rule, after the person that discovered it. And it's called 4n plus 2. People get confused. Mathematicians, you're going to be okay. You're used to this kind of nomenclature. N is an integer from 0 and so on. N does not equal the number of atoms in the cycle. N is just a regular increment, okay? So the allowed number of electrons you can have and be aromatic allowed or right number of electrons includes 2, 6, 10, and so on. The reason for this rule, here's the 2, here's the 4n. Right? In any system of pi molecular orbitals in a cyclic system like this, you're always going to have one lowest energy orbital that can accommodate 2 electrons, and then you're going to have pairs of degenerate orbitals at higher energy levels that each individually can accommodate 2 electrons, but since there's 2 of them, you get 4. And if you have 2 or 6 or 10 electrons, you can fill the lowest energy one and then the pairs of degenerate higher energy orbitals moving upward. As a mnemonic device, there's something here except I can't spell that word. Mnemonic device is called the frost circle. And what you do is you draw a circle. That's lovely. And then you draw a hexagon, then you draw the ring shape of the molecule you're interested in. In our case, it's benzene. You draw it with the point down, and then you just inscribe a regular polygon, hexagon, on the, oh man, really terrible at that. Ooh, that's kind of nice, isn't it? Okay, and you draw a hexagon and inscribe it on the circle. Every place where the hexagon meets the circle is the location is the location of an energy level. And that's your MO diagram for benzene, without knowing anything about actually the math. And this actually works pretty well quantitatively if you do the geometry. The actual distance here between this lowest energy one and the next higher degenerate pair is accurate, which is so sort of kind of wild.
Like
But
it actually is accurate or is pretty close?
proportional, it's accurate. Yep.
Wow, that's really cool.
Yeah, don't know why. And then, so without even knowing what the shapes of these orbitals are, like we've drawn here, you can use the frost circle to get an idea of their relative energy levels. Let's see, it looks like, trying to find the, dang it. Need to find the midpoint of the circle, which should be 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, great, I chose. All right, so if you find the midpoint of the circle and you draw a horizontal line, that horizontal line, which doesn't look that horizontal, but whatever, that's the zero energy point. That's the energy of a non-bonding p orbital. So you can see that one of the interesting features of this is just that, well, anyway, you can get a sense that the two degenerate pairs are this much lower than the non-bonding line, and then you get bonus stabilization for the one that has no anti-bonding interactions whatsoever. And then you can fill them up with the available pi electrons. We're going to use this device to look at some other systems to determine whether or not they're aromatic. But you can do this with polygons of any size, so triangles. The only thing, that's the only polygon I can think of. Triangles, squares, pentagons. The bottom point always has to be downward though, because no matter what size cycle, you're always going to have one option where everything's all overlapping with bonding interactions. Okay, so let's take a break. We're going to come back and work through, is it aromatic or is it not? By the way, it's so easy to write multiple choice questions about this. You can expect there to be a lot of them. They are really easy to answer if you put in your work. So it's like 3 points on the table, people. So yeah, come back, we'll get going. All right, friends, hope you had a good weekend. I think we were, let's see, talking about the second of these horrible challenge problems. Our goal was to help you not panic when you see something that's unfamiliar. And sometimes we get used to the idea that we want a rote procedure that we can memorize that will take us through and get us the right answer every time. And organic chemistry just isn't really that way. If you see a problem like this, you think, how was I supposed to know what to do? The answer is you weren't. But you were supposed to dink around with it, draw a few pictures, try to find anything that looks remotely familiar to something you've seen before and see where it takes you. So, as I recall on this problem, we start out with this strange 6-membered ring with lots of things on it, an epoxide, an ester, and then another ester but connected through an oxygen to the rest of the molecule. And we see one of these horrible bridged bicyclic products as the product, and we've got to push arrows to get from here to here. This is one of the challenge problems straight out of chapter 18. We look for things that didn't change, so I see this allyl group, or this alkene. I see this methyl group here, same stereochemistry. Interestingly, in the position where the epoxide used to be, I see an oxygen and then something else, sort of this 1-2 pattern of OH group and nucleophile that you can get if you open an epoxide. All right, so let's try to figure out what I don't see, what's missing here. On this, I still see the orange oxygen, but I'm almost entirely missing this ester group. In fact, and I'm also missing a methyl group. It almost looks as though, I'm running out of colors here, maybe we'll go purple. It almost looks as though that methyl group somehow ends up there. And then, not that clear where everything else comes from. Other than it's possible, I suppose, I definitely don't have this methoxy group present in my molecule, so I need to lose this. As we said, I need to open the epoxide here. But I suppose it's possible that, I'm running out of colors. I guess it's possible that this carbon is here. So, all right, let's sort of think through this. And in fact, it may be useful for us to think backwards strategically. Since of all that we've got going on here, opening of the epoxide seems to be the clearest thing. Let's think backwards one step from epoxide opening, all right? So we can just sort of copy this. And in red is the bond that I would have made from epoxide opening. So that means this would have been the nucleophile, and then the epoxide from our perspective is going to be here. Does that look good? Okay. Okay, tell me about this. What does that look like? I could draw a resonance structure. Anything wrong with that? Okay. Good. So now I'm sort of one step closer, right? Because I can open up the epoxide like this. And then that would result in a structure kind of like this with a negative charge on that oxygen, which I could which I could protonate. This is a beta dicarbonyl compound, right? And I could have gotten that from its precursor. In other words, I could have gotten that from just the corresponding enolate by deprotonation of this alpha carbon. All right. Functional group wise, this is a beta keto ester. Now there's a reaction you've learned in chapter whatever this is, 18, where the product is a beta keto ester. Remember what it is? Exactly, it's the Claisen reaction. Take one ester enolate and you attack to get the tetrahedral intermediate. Once you get there, there is a leaving group decent enough relative to a negatively charged oxygen to leave, and then that gives you the beta keto ester product. So which side of this beta keto ester, the bond that I would have made is this one between alpha and beta carbons. That means this used to be my nucleophile and this used to be my electrophile. So thinking backwards one step, you want to, let's see, if this used to be the nucleophile on the alpha carbon, there's the enolate, the electrophile, and now we start looking at the starting material to see, okay, that's where our methoxy group went, right? We attacked to get a tetrahedral intermediate, and then that methoxy group kicked off, okay? So presumably the first step of all of this is some base. Probably doesn't need to be LDA. It probably can just be a cheap base like hydroxide or sodium ethoxide, because as with the Claisen reaction, you make the enolate, you attack to get the tetrahedral intermediate, which I guess we can draw. Oops. Then electrons kick down and the leaving group leaves. And that gives you your beta keto ester. As soon as you've made that, you've got these very acidic protons, pKa around 13. So whatever your base is, it doesn't need to be very strong because you quickly remove this proton to make the enolate. And that's, 100% quantitative yield. And then once you make that enolate, the oxygen here is held close enough to the epoxide. And this is an unusual step. This is a step we haven't seen before. Normally we've done enolate alkylation at the alpha carbon. This is an example where, for whatever reason, because the oxygen's close to the epoxide, you alkylate the oxygen with your electrophile. Now, would you have been able to predict that? Probably not, because I told you we normally alkylate enolates at the alpha carbon. Could you predict, or could you explain or understand how it happened, given the fact that it did? Well, yeah, your goal is to get to this point, and then there's no other choice to get to your desired connectivity. All right, any questions you want to ask about the thought process there? You're dealing with some ambiguity. I know you're uncomfortable with that, but welcome to adulthood. All right. So if you want to test your skills at this. Don't be afraid to try some of those ugly, horrible looking challenge problems. You may find along the way that you're having just a little bit of fun as you realize that something really complicated is actually made up of some steps that you can see and understand. All right, so we need to move on to the next chapter, which is on benzene and aromaticity. And maybe this is best illustrated by a couple of examples. You've seen before that if you take an alkene and react it with HBr, you get an addition product in which you've added HBr across the pi bond, where the pi bond acts as a nucleophile, and you make a carbocation intermediate where the carbocation's on the more substituted carbon where it's more stable, and then in a second step, Br minus can come in from above or below, attacking the carbocation to give you the addition product. We didn't necessarily talk about this at the time, but you've probably seen examples of reactions that involve benzene rings where nothing happens to the benzene ring. So you can take HBr and benzene and nothing happens. Benzene sort of just stares at you. It chooses, or rather it just does not react with HBr, which is confusing if you understand benzene to be 3 double bonds in a ring, 3 isolated double bonds, because alkenes should be reactive to HBr, and yet benzene is not. So historically, people looked at benzene and said, it's got some kind of unusual stability. That's not what you would expect given the reactivity of a pi bond. Now there's some other things going on with benzene as well. For example, if you look up bond lengths in organic molecules, you find that double bonds are shorter than single bonds by a significant amount. Nevertheless, benzene's structure is not, and I wish I had the numbers in front of me, I don't have them, but benzene's structure is not short double bond, long single bond, short double bond, long single bond, short double bond, long single bond. In fact, all of the bonds in benzene are equal in length. And this is reflected in the fact that benzene has 2 resonance structures. They look identical and they vary only in the position of the double bonds. So you can't look at benzene and say which carbons are involved in pi bonds, or rather which carbons are pi bonded to each other, because if we number the carbons 1, 2, 3, 4, 5, and 6, are the pi bonds between 1 and 2, 3 and 4, 5 and 6, or are they between 2 and 3, 4 and 5, and 6 and 1? And the answer is yes. So resonance is an important part of benzene's unusual stability. Resonance delocalization of electrons is stabilizing. But there's even a little bit more going on with benzene than just that. As evidence that all of the bonds in benzene are equal length, if you do the NMR spectrum of benzene, the proton NMR spectra for benzene has just one signal. There's only one kind of proton in benzene. And the C13 NMR spectrum for benzene has, again, just one signal. There's only one kind of carbon in benzene. They're all identical. So that gives you some idea of the fact that resonance stabilization makes all of those carbons identical. All right. To understand where benzene special stability comes from, you need to know a little bit about MO theory. So let's see. Questions you want to ask so far? Bored to death? Okay. So I don't know if you recall, we've talked about the allyl cation or the allyl anion situation at some length in the past. We talked about how you learned about conjugation in 351, and you would have learned that conjugation involves a consecutive string of p orbitals on adjacent atoms that can line up with each other and form an extended system of pi molecular orbitals. Some of you, and this is review, have thought about pi bonds as being side-by-side overlap of two p orbitals to give you a filled pi bonding orbital. Here we're using shading to indicate sign of the wave function. I don't want to say any more about that. If it's confusing to you, you should go look at the optional molecular orbital theory review study guide. The side-by-side overlap of two p orbitals creates a pi molecular orbital, and this is a bonding orbital. It's more stable than the p orbitals that you start with, and then we create an anti-bonding orbital where the wave function sign switches between carbon atoms 1 and 2. The place where the wave function goes to 0 is called a node, and there's no electron density along the node. We call this the pi star antibonding orbital. And of course, for an isolated pi bond, you've got electrons in the pi molecular orbital, no electrons in the antibonding orbital, and this is a covalent bond. You can, if you want, you can put a dotted line roughly at the energy level of the p orbitals that you start with to make the pi bond. When the math of MO theory requires that when you add two molecular orbitals together, add two atomic orbitals together, you get two molecular orbitals out. This is the plus combination, the p plus p combination, and this is the p minus p. We've thought about this as constructive interference, and this is destructive interference of electron waves. If you go to the slightly larger system of pi orbitals present in the allyl cation, you're going to have three different molecular orbital combinations that come out of this. You mix three atomic p orbitals together to get three pi orbitals. One of the lowest energy combination is sort of the p plus p plus p combination. That is all three of these on adjacent atoms together with the same wave function sign. There's also higher in energy, the all out of the p minus p plus p combination where wave function sign alternates in between each carbon such that there is a node or a place where wave function sign goes to 0. And then at an intermediate level, there's a p minus p combination where there's actually a node that coincides with atom 2. Okay, so you have 3 pi molecular orbitals. We dropped the pi star sort of indication since we've got 3 of them and just call them 1, 2, and 3. In the allyl cation, we have 2 electrons involved in the pi system, so only the lowest energy orbital is filled. The next one, the lowest unoccupied molecular orbital, or the LUMO, is on carbons 1 and 3, but never on carbon 2, which is exactly what resonance tells you where the positive charge is. That should be maybe mostly review. Questions you want to ask about that? Okay. The point is you can mix more than 2 p orbitals together to get more than 2 pi molecular orbitals. Notice that the more nodes an orbital has, the higher in energy it is. So our lowest energy pi 1 has 0 vertical nodes. This one has 1, this one has 2, and that tells you the relative energy levels of each of the orbitals. So now I want to do the same thing for a slightly larger conjugated system. This is a molecule with 6 atoms. This is 1,3,5 hexatriene. Okay. And what happens when you combine 6 p orbitals together? You're going to get 6 pi molecular orbitals out. And figuring out what these orbitals look like is actually pretty easy, but I never ask you to do that. At most, I ask you to be able to count the number of nodes in a diagram of an orbital that I show you and rank them in energy and decide which one is the HOMO or the LUMO. So what we're going to do here is I'm just going to show you what these orbitals look like. There are 6 of them. 1, 2, 3, 4, 5, 6. Good enough. We'll call them pi 1, pi 2, pi 3, pi 4, pi 5, and pi 6. And I'll draw them for you. And actually what we're going to do to save ourselves a little bit of time and a little bit of drawing time is we're going to imagine looking down on these orbitals as though we were above them, right? So if I were looking down on this orbital, what I would see is carbons 1, 2, and 3. I would see a continuous lobe of electron density above the plane of the page, and then behind the plane of the page I'd see another, and it would have opposite wave function sign, which I'm representing by color. But I could represent that schematically as just the top lobes of each of these all together. One thing that's confusing for people that when dealing with this is I don't mean 3 adjacent p orbitals here. I mean 1 molecular orbital extended over all 3 atoms. The better way to draw this orbital is just like this, but then I'd have to indicate the positions of the atoms so you wouldn't get confused. And so to avoid that, it's traditional among organic chemists to just draw a p orbital on each carbon that's involved in the molecular orbital, and where the 2 orbitals are side by side without a change in wave function sign, you assume that the orbital spans the space between those 2 atoms. Okay? That's sort of a dumb nomenclature issue, but I've seen people get tripped up over that. When you look at that, you need to not be thinking, oh, 3 p orbitals. You need to be thinking 1 pi molecular orbital. All right. So I'm going to just save ourselves some time by drawing the top-down view of the orbital, but with those sort of adjacent circles. So if this is carbons 1, 2, 3, 4, 5, and 6, the lowest energy orbital for our 135 hexatriene is going to be one that spans all 6 atoms with no change in wave function sign between the atoms. The next one is going to be a combination that has only one node, and this node is going to be between atoms 3 and 4, such that there's a change in wave function sign as you go from atom 3 to atom 4. Understand that if you were to actually see this molecular orbital on the molecule, it would look like this, with a node in the middle. And we're looking sort of still from a top-down view. Okay, and so we can continue. You basically, in generating these, have to just find ways to put one node or 2 nodes or more in a symmetric sort of fashion. So the 2 node situation would look like this. There would be a switch in wave function sign between carbons 2 and 3, and again between 4 and 5. If you're following along with 135 hexatriene, we've got 6 electrons involved in the pi system. That is 6 electrons involved in the pi bonds that are conjugated. All 3 of these lowest energy orbitals are filled, and so we can continue onward, coming up with the rest of the empty pi molecular orbitals. The highest energy combination is going to be one where there are switches in wave function sign between each of the atoms. And then let's see, 3 nodes. We're going to have 1 in the middle, and then there. And then 4 nodes we have here and here, here and there. All right. Okay. So, in addition to looking at the number of nodes to rank orbitals in terms of stability, you can get a sense for how low in energy an orbital is by looking at the number of times in that orbital that adjacent atoms have the same wave function sign. Going back to the original pi bonding molecular orbital, this pi bonding molecular orbital is bonding because if you put 2 electrons in this orbital, they would tend to stay between the 2 nuclei and draw the 2 nuclei together. Whereas if you put 2 electrons in this anti-bonding orbital, they're not going to spend time in between the 2 nuclei. So they're not going to contribute to bonding of those 2 nuclei together. In fact, anti-bonding orbitals are actually biased a little bit towards the space away from the nuclei, though I haven't drawn that here. So any time in one of these orbitals you have adjacent atoms with the same wave function sign, that's what we're going to call a bonding interaction. And so this lowest energy pi molecular orbital pi 1, as I said, every time you have 2 atoms adjacent to each other with the same wave function sign, we're going to call that a bonding interaction. I don't know why. There we go. Whereas if you're going to have 2 orbitals adjacent to each other with the opposite wave function sign, we're going to call that an anti-bonding interaction. Okay? So, going back to our pi and pi star, we would say that our pi molecular orbital here has one bonding interaction. And that our pi star has one anti-bonding interaction. Really, this is just bookkeeping to determine the relative energies or strengths of these bonding orbitals. So our pi 1 bonding orbital has 5 bonding interactions. Now compare that to the pi molecular orbital from the single double bond. That doesn't make any sense. The individual double bond. You see 1 bonding interaction here, you see 5 bonding interactions there. That's a good way to predict that this pi 1 orbital here is quite a bit lower in energy than just an isolated pi bond. And you can figure out what that number is, you can calculate it, and it's substantial. This is what we mean by resonance stabilization. Delocalization of electrons is favorable, and you can tell that because having 2 electrons delocalized over 6 atoms in this fashion is more favorable and lower in energy than having 2 electrons delocalized over 2 atoms. Okay? We could put numbers on this, but just counting the bonding interactions is good enough. Yeah?
Yeah, just taking this to benzene, does that mean if we put in a ring it would have 6 bonding?
There you go. Yeah, exactly. So we're about to do this, but you're going to get bonus in benzene because if you cyclize that orbital, as is the case, if you arrange things in a cyclic fashion with benzene, because in 1,3,5-hexatriene, carbons 1 and 6 cannot be adjacent to each other, but they're forced to be adjacent to each other in benzene, then yes. In benzene, that lowest energy orbital is going to have 6 bonding interactions, and that's even more favorable. And that's the extra stability you get from benzene. Yeah. So we don't need to actually belabor the point too much. This pi 2 molecular orbital has 1, 2, 3, 4 bonding interactions and 1 anti-bonding interaction. Anti-bonding interactions offset bonding interactions, so we're going to call that 3 net bonding interactions. The pi 3 molecular orbital has 3 bonding interactions and 2 anti-bonding interactions, so 1 net bonding interaction, and so on. We can see 1 net anti-bonding interaction here, 3 net anti-bonding interactions here, and then 5 anti-bonding interactions here. All right. So we did all of that just to give you the sense that, think of it this way, if I had 3 isolated pi bonds, the energy from that would be basically 3 bonding interactions, because each pi bond has 1 bonding interaction. You connect them via conjugation, and you get something that's much more stable than the isolated, than 3 isolated pi bonds. So you get some bonus stability. Now think about what we've drawn here is the pi 1 molecular orbital for benzene. And instead of having only 5 bonding interactions, because it's cyclic, you have 6 bonding interactions. So that's almost an entire bonus pi bond of stability. Relative to that's almost an entire bonus bonding that's 1 bonding interaction of stability relative to 1,3,5-hexatriene by making it cyclic. Okay? And what that means is the pi electrons for benzene are held lower in energy than you would expect for 3 isolated pi bonds, and so they're less reactive. All right. Questions you want to ask about that? All right. I want to show you the other molecular orbitals that come out of the math for benzene, because these molecular orbitals are important for understanding how to identify molecules like benzene that have this special stability. So it turns out, and I'm going to do this here. The next highest combination actually you can get simply by cyclizing this pi 2. So we'll draw an orbital like this. You have 3 of them with one wave function sign, 3 of them here, and you have a node that basically spans the 2 atoms, or spans the space between these 2 atoms and these 2 atoms. Okay, so just one node. Now, it turns out that the math of MO theory gives you another combination where you still have just one node, but instead of having the node be between the 2 atoms, you have the node actually coincide with 2 of the atoms. So I don't know how we're numbering things. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. In the molecular orbital that I'm showing you here, the node actually coincides with atoms 1 and 4. However, if you look at the number of bonding versus anti-bonding interactions, these 2 orbitals are actually identical in energy. So the one on the left, you have 4 bonding interactions minus 2 anti-bonding interactions to get net 2 bonding interactions. The one on the right, you have 2 bonding interactions and no anti-bonding interactions. Anti-bonding interactions only count when 2 adjacent atoms have opposite wave function sign. Because the node coincides with atoms 1 and 4, it sort of splits the molecule into 2 separate parts. So this orbital has just 2 net bonding interactions. Okay? So that means that in benzene we have one lowest energy orbital. That's the one that's cyclic. Sorry, that's the one where there are no nodes. Everything is on, sorry, there's something on my